Hello, hello. How you two doing?
Oh, no. Oh, oops. Oh dear. I need to disconnect thing from my. Yeah, I need to plug in my headset first. Oh shoot. No, never mind. Just get connected here.
Tyler, do you plan to go to this tea tomorrow?
So the tea with Bianca, right? Right.
Mhm.
Yeah, I was not planning it, but okay, so hmm. It cuts, well, we can go for a short time if we do go. It cuts through Sasha's talk.
Yeah, there's a lot of stuff tomorrow.
Yeah, I know. Yeah, there is one after another. How about you?
Yeah, I don't know. I'm thinking about it. I just saw Daniel's email.
Yeah. Yeah, that'd be interesting.
Hey, we're talking about the tea with Bianca Varai.
Yep.
Yeah, it's unfortunate. It seems like our class is scheduled so that we'll miss almost all of it. If anybody wants to, bail out and go to the tea, it's fine. It's
Oh no,
fine.
I think it's tomorrow, not
Wow.
Oh,
Wednesday.
it's tomorrow.
I
Oh,
believe, unless I
Tuesday.
misread.
Oh, that would make more. No, it's Tuesday, which is tomorrow. So you're right.
Okay, cool.
All right. Well, that makes okay then. Then I guess I can go actually. Yeah. So her talk sounds really good too. She's an excellent speaker. All right. Are there any questions? Well, if not, it's time for what in my notes is called lecture 17. So, it continues. Let's see. Yeah, we're really going to get into the nitty gritty of the local class field theory today, which remains somewhat technical in its aspects. So yeah, so this, you'll sort of see where, oh yeah, maybe just last time I mentioned these two facts. The first fact is it's a little specific and detail oriented, but among other things, it's telling you that the cohomological dimension of a local field is 2, which is important if you're thinking about just Galois cohomology of fields. This would be of more significance if we were going to go on to study local duality theorems, which are the sort of thing that I mentioned briefly in the last lecture. And so yeah, there's this chapter 10 in Harari's book, which is on local duality theorems. Anyway, but we're not. So this would be straightforward to prove based on what we know, and then anyway, I think I'm just going to move on at the moment and not prove these things. I could come back if all of a sudden I have more time than I was expecting. This is certainly a very useful result in practice. So again, this is saying that whereas before we saw that was not a very deep result, that if you have Galois cohomology or group cohomology of a finite group acting on a finite module, then all of the cohomology groups have to be finite, even because of the cochain groups are finite. Right, but here we're saying that this is Galois cohomology of a definitely infinite profinite group, but the fact that the fact that the Galois group is small in the sense of, yeah, maybe I should go back and it's been a little while since I thought about this, but I think I'm pretty sure that if in place of a p-adic field, you were to take any any field whose absolute Galois group were small in the technical sense that there are only finitely many open subgroups of any given index, or equivalently on the field theory side, there's only finitely many inside a fixed algebraic closure, there's only finitely many separable extensions of any given degree, unless I'm really misremembering the way things work, that itself should be sufficient for Galois cohomology with finite coefficients to be finite. Again, this is not true for a Laurent series field. If you go at P, it's not even true if you take like H1 with coefficients in mu P. By Kummer theory, that's parameterizing P power classes, K star mod K star to the P. And as I mentioned and left as an exercise, whereas the group of nth power classes is finite in any p-adic field, and it's still true in any Laurent series field over a finite field as long as n is prime to P, the group of p power classes of the Laurent series field is infinite. Okay. Right. Okay. But yeah, so I think we just need to press on. Okay. But yeah, no, this is a really the fact that the absolute Galois group of a p-adic field is small is a main difference between local class field theory and global class theory. The absolute Galois group of a global field is not only just not small, it's kind of the other thing. It's a global field is a Hilbertian field, is a field to which Hilbert's irreducibility theorem applies. And so conjecturally, the inverse Galois problem should have such a strong conclusion or such a strong resolution over any Hilbertian field. If you pick any finite group, there should be like infinitely many pairwise linearly disjoint Galois extensions with Galois group, whatever finite group that you want. And we can certainly prove that for lots of finite groups, finite commutative groups over any global field. So the Galois groups of global fields are really big in the Galois groups of p-adic fields and Laurent series fields, as long as you stay away from P, are really small. I mean, it's still infinite, but small. Okay, so let's go ahead with the actual, yeah. So the result that I want to prove today is what I was saying. This is if you plug in Tate Nakayama to everything that we've already done, you just get a result which you look at and you say, this is a big piece of local class field theory. Okay, so we have our local field. Until further notice, K denotes a local field. So let's take a degree n Galois extension with Galois group G. As we'd already mentioned, we computed the Bauer group of a local field, not just absolutely, but also relatively. And so the restriction in any finite extension of local fields gives you some map from Q mod Z to itself, and that map is always multiplication by the degree. And so therefore, the set of classes that are killed by, again, by restricting from K to L, you're multiplying by N, and so therefore the kernel is the N torsion in the Bauer group of K, but the Bauer group of K is Q mod Z, so its N torsion is the cyclic subgroup of Q mod Z generated by the class of 1 over N. Okay, so in particular, there's, yeah, I guess I'm putting a name to this. This is called the fundamental class. So there's a certain class in the Bauer group, which again can be viewed as this relative Galois cohomology group. So again, 1 over n z mod z is a cyclic group of order n with a canonical generator, I guess, to be really precise. It's the 1 over n plus z, so that coset. And so under this invariant isomorphism, that was the main thing that we proved. We had a canonical isomorphism. So there must be some Bauer class that map whose invariant map is the class of 1 over n. And we call that the fundamental class. And then just this idea, this Tate-Nakayama stuff says that if you have a couple axioms that you satisfy, then cupping with the fundamental class, so it's that class which satisfies some axioms, will induce isomorphisms on your Tate cohomology groups. And so we are in a position to apply that. So my claim is that the Tate-Nakayama theorem applies here, with the coefficient module being L star, and then the class being this fundamental class. It's been a little while. What was Tate-Nakayama? So again, taking advantage of the format, we can literally flip back to page 5 of lecture 10. So what was Tate-Nakayama? This was Tate-Nakayama. So we have a finite group. A is a G module. We have a certain kind of abstract fundamental class, really cool cohomology class, H2, with coefficients in A. And so what are our assumptions? Our assumptions are some kind of abstract Hilbert 90. That's the way you view this one. It's going to be true in our context by Hilbert 90. So the first Galois cohomology of all the CeLO P subgroups with coefficients in A should be equal to 0. And then the second cohomology, the size of it should be equal to the size of this CeLO subgroup. Again, that's definitely going to be true in our context from what we know about the Brauer group of a local field. But moreover, we want, again, these are kind of the local ones. And so we want this not just to be a group of order the size of the CeLO P subgroup, we want it to be a cyclic group of that size. And moreover, we want it to have a canonical generator, which is obtained by restricting this element to the CeLO P subgroup. Okay, and so I mean, I'm just recalling it for you, but it's going to be pretty much immediate that that the fundamental class has these properties. So what do we get if all this holds? Then for all torsion-free G modules and all subgroups, I think we're not going to mess with subgroups in our application. I think we're just going to take G itself. Then cupping with the fundamental class gives you an isomorphism in Tate cohomology. In particular, if you just take what's your favorite torsion-free G module, probably the integers with trivial action, okay? And so in particular, and again, I'm even going to take this, I think, with H equals G, and we'll get an isomorphism. So cupping with the fundamental class will give us an isomorphism from the nth Tate cohomology with coefficients in Z to the n plus second Tate cohomology with coefficients in whatever this module is, but this module is going to be L star, the multiplicative group of the upstairs field. Okay. So let's check that it actually applies. So again, this is quite, I mean, it's almost immediate. So yeah, so this GP, same as before. So when you restrict to a CeLO P subgroup, you do the Galois theory thing, your top field is the same. And then the only thing that happens is that the bottom field K gets replaced by, well, the fixed field of GP in the Galois theory sense, but that's still an instance of relative Hilbert 90. And so great. So the first one is equal to 0. Same down here. If we do this, then again, the only thing that changes when we switch from G to GP is that the ground field switches from K to whatever that intermediate extension corresponding to Galois theory gives you, and everything works just as well. And so, yeah, so we know that if you have any sort of relative Brauer group of a finite Galois extension of local fields, then it's cyclic of order equal to its equal to the size of the group, equivalent to the degree of the extension. And we have this fundamental class, right? So okay, so it does have the right size, and well, what's going on? Again, we know the Brauer group is the invariant map is a canonical isomorphism to Q mod Z, and then if we take our fundamental class, then under restriction, it just gets multiplied by the degree. And so sure, whereas our fundamental class was like 1 over n, where n was the degree of L over K. If we restrict, I mean, let me just call it what it is, I guess, LGP. Okay, and so this has degree n, and this one is, I don't know, NP, the largest power of P dividing n. Right. And so, yeah, and so if I take this class that has order n, and then I restrict it to this extension that has degree, so obviously the degree of this is n divided by np. And so therefore I took some element, it's kind of hard to read, but I guess you can see what it is. So yeah, so I took this element that had order n, and under restriction, it literally gets multiplied by n times by n divided by np. So if you take an element of order n and you multiply it by n divided by np, it has order np, but the whole group has order np. It's fine. Okay, so this is the least of our worries. Okay, so we correctly verified the hypotheses of Tate Nakayama. And again, I mean, of course, like there's the words like class formation are used to describe this kind of abstract setup. So something similar is going to happen in the Galois cohomology of global fields. It's just that the module is not going to be the multiplicative group anymore. Some idels are going to be used instead. But my understanding is that the class field theoretic setup came first, in several contexts, two different kinds of local fields, two different kinds of global fields. And then sort of Tate, came up with this quadratic way of doing it. And then Nakayama came along and said, well, actually, you can phrase all of this abstractly in terms of group cohomology. And that was the Tate Nakayama lemma, but it's sort of like the application came before the general theorem, is my understanding. Okay, so we have the conclusion that we get. So here I'm just rewriting the conclusion from the Tate Nakayama theorem. But what do we really want? We really want to take d to be z, and in fact the n that we really want is -2. So okay, cupping with this magic fundamental class is going to give us an isomorphism from -2nd Tate cohomology with coefficients in z to 0th Tate cohomology with coefficients in, well, z tensor A, which is L star. Okay, well, what are these two cohomology groups? This one must be very familiar to us at this point. So Tate H0 is the invariance module of the image of the norm. So that's the co-kernel of the norm map. We've been seeing that for a while. What about Tate minus H2? Tate minus H2 is regular H lower 1, the first homology, but the first homology with coefficients in the integers. This was one of the very first calculations that we did using augmentation ideals and stuff. And it's also isomorphic to the augmentation ideal modulo its square. And then you check that there's a canonical isomorphism to the abelianization of the Galois group. Okay. So that's a big theorem, is what we get. So just for some bookkeeping, always bookkeeping. So that isomorphism, I'm following Harari, he calls capital theta of L over K. And then for various reasons, it's a little bit nicer to look at the inverse of the just functional inverse. Go from target back to source. And so we say omega L over K is the inverse function, which is also a group isomorphism. And this is this is a very interesting deep result about the Galois theory of local fields. Namely, if you have any finite Galois extension of local fields, it doesn't even have to be abelian yet, with Galois group G, what can you tell me about the image of the norm map? Is the norm map surjective like it is for a finite field? Yes. If and only if the abelianization of the Galois group is trivial. So in fact, it might be surjective. This is a deep result. What if the Galois group were like, I don't know, like A5 or something, some finite simple group, then its abelianization would be trivial, but not if it's a finite abelian extension, right? So in particular, if this is a finite abelian extension, then the co-kernel of the norm map is actually isomorphic to the Galois group itself. So that's pretty exciting. Yeah. Okay, so yeah, that's like some percentage of local class field theory right there. We would like to go for more. I mean, yes, there's most of this, to be really honest, most of this lecture is kind of technical stuff with characters and compatibility of cup products under various maps and that sort of thing. And then I'll show you, there's even one proof, not this one, but the next one. I stared at it for a long time last night and I was like, I'm just not sure if you've given all the details of this proof. The result is definitely true. But anyway, so we'll see. This lecture is a bit technical. And then, yeah, maybe I should skip forward a little bit just to see. Yeah, so this is where I'm going. So we have an isomorphism for every finite abelian extension K. We have an isomorphism from the co-kernel of the norm to the automorphism group of K. Again, in general, it would be the abelianization, but I said it was abelian. Okay, and then assuming some nice functoriality, I can pass to the limit on both sides, and one of the technical results will say that these isomorphisms are compatible with the maps that you have in both directions. Okay, so not only are any one of these groups isomorphic, there's a natural inverse system here, and the isomorphisms are compatible with the inverse system. That's what I'm going to state and get slightly stuck on the proof of, following Harari. But anyway, once you have that, well, this inverse limit, what's the inverse limit over all the finite abelian extensions of the automorphism groups of the finite abelian extensions? Well, that's nothing else but the absolute abelian Galois group of the field, namely. So you can think of this either as the abelianization of the absolute Galois group, so mod up by the closure of the commutator subgroup, or literally you have, so if you have any field K, you have K, and then you have the separable closure here, and then you can just put, the compositum of finite abelian extensions is a finite abelian extension. So there is a unique maximal abelian extension of any field inside abelian Galois extension inside its separable closure. And if the Galois group of the whole thing is the Galois group of the whole thing, GK, then this is GKAB. Okay, and again, GKAB really is, it's almost just the normal commutator subgroup, but we're doing profinite group theory, so we should, whenever you mod out by a subgroup, you should either prove that it's closed or take its closure, and here you do need to take its closure in general. Okay, all right, so that's what's happening on this side, and then on this side, well, this is just a very interesting thing. Like this is now this is something that looks like it might be the profinite completion of K star is kind of what you're getting here, right? So here this thing here is definitely going to be a profinite group, because again, all these guys are finite. In fact, whatever this thing is, it's going to be isomorphic to that, right? But so you see what we're doing, we're taking the inverse limit over the quotients of the co-kernel of the norm subgroups, okay? So whatever else is going on, I definitely have a map from K star into the inverse limit. Why? Because I have a quotient map from K star into each one of these finite quotients, and definitely the K star, again, I'll talk a little bit more about what the maps are here. It's easy. And so, yeah, so just by the usual universal property of the inverse limit, I have a map from something into each one of these guys compatible with the projection maps, like if that's what you want to call them. And so there's a unique homomorphism into the inverse limit. And you think about it a little bit, because I'm taking the inverse limit like this and giving each one the discrete topology, sort of the canonical topology on the inverse limit is the one where the open subgroups are precisely the norm subgroups. And so because K star surjects onto the quotient by every finite open subgroup, if you think about it for a little while, that's telling you that that the image of K star is definitely dense in here. And so yeah, that's what I just wrote there. And so then you kind of ask yourself the question, well, I don't know, maybe I'll let you think about this. If I've just told you this, and I've told you I have a map here to this inverse limit, this is an isomorphism, so this inverse limit really is isomorphic to the abelianization of the Galois group of K. And now I'm looking at this map. K star itself is a locally compact, not compact topological group. right? Because essentially because the valuation can be whatever it wants to be, which is kind of unbounded, right? The elements of valuation 0 are compact and profinite. So what might you ask in this situation, having seen this much? Another way to put it is like, what else should I tell you in order for this to be like a class field theory? Well, I have a map from a totally disconnected locally compact group into a profinite group, which is isomorphic to the profinite group that I care about. So I'm trying to get a better understanding of this profinite group. This profinite group is isomorphic to this profinite group. And then I have a map from this guy, which looks, much better understood. Class field theory is supposed to be a description of a billion extensions of a field in terms only of data of the field, right? So maybe I should be asking, this is an isomorphism, so that's telling me everything I need to know. I kind of want to know more about this map, but can you see like what I haven't said yet or what I might want to know about it?
You mean the kernel of this map, or?
Yeah, that's a good, yeah. So one question is this map injective, right? I said it was dense, which is close to, it's kind of a topologically appropriate analog. So yeah, so one question is this map injective, right? Is there a more, fancy, using the language of profinite groups, is there like an even crisper question you can ask? So again, this is a topological group. This is a profinite group. I have a map. It's definitely not profinite because it's not compact. And I have a map into a profinite group. It's dense. So if you have a dense map from a topological group into a profinite group, you're entitled to ask what? I would like to know whether this map is a profinite completion. That's my question. In other words, is this the universal map from maps? Is this universal for maps from this topological group into a profinite group? Like that's the categorical way of saying it. What's a more algebraic way of saying it? Well, Menzel's question, is it injective, is a key question, right? So the obvious question I said is this map a profinite completion? But what are we really asking? We're kind of asking, are there enough finite abelian extensions in order for the norm subgroups, the image of the norms, to define the topology on K star? So that's the question. For this map to be a profinite completion, and even for it to be injective, there need to be enough of these norm subgroups. And so really what we're asking is, are the norm subgroups cofinal among open finite index subgroups of K star? So, or even better, is every open finite index subgroup of K star one of these norm groups? Right? Because what is the profinite completion of any topological group? It's exactly the inverse limit to the quotients by open finite index subgroups. Right? So that's the question. So somehow, so somehow the question, this is a lot if we know this, but now we're wondering whether we have enough abelian extensions. Okay, so we can we're parameterizing our abelian extensions faithfully via certain subgroups of K star. That's exactly what we've done so far, right? For every abelian extension, I give you a subgroup of K star, the image of the norm map, and it does follow from, I mean, if you think about it, it has to follow that the map that associates to a finite abelian extension the image of the norm map, that has to be an injective map, because if you take the compositum of two different finite abelian extensions, you're going to get a bigger finite abelian extension. And so if their norm maps were the same, then that wouldn't happen. Right. So that's the idea. So the idea is that I've faithfully parameterized abelian extensions by certain open finite index subgroups of my topological group. That's very nice, but I'm trying to like construct finite abelian extensions. So I want to go the other way. Do you see what I'm saying? So the remaining issue here is, do I have like exactly as many finite abelian extensions as I have open finite index subgroups, or is this group not the full profinite completion of K star? Is it only a proper quotient? Okay, so that's called the existence theorem, which basically says you have as many abelian extensions as you want to have, and then another way of saying that again would be to say that this it's called the reciprocity map gives an isomorphism from the profinite completion of K star to the abelian Galois group of K. Okay, so that's where we would be going afterwards. Okay, but any questions about that? That's probably more important than all the technical stuff I'm going to say in the rest of the lecture. Okay, so that's the idea. That's sort of what we've done so far. But then we have to, everything that we've done so far is not telling us how many abelian extensions there are. It's only saying if you give me an abelian extension, then I can connect it with norm subgroups. Okay. All right, so let's go back and yeah. Okay, so next proposition, a little bit technical, but useful. So now my extension is going to be abelian. So the Galois group is of course going to be its abelianization, and then I have a character. Okay, just continuous homomorphism to Q mod Z. For some reason, I'm writing D of chi for the image of chi under this. I mean, again, the character group is this. This is trivial module, so this H1 is just a continuous hom. And so this, as we've seen before, this coboundary map is an isomorphism because the other coefficient module is Q, which is acyclic all day. So this map is an isomorphism. Yeah, I don't know. I think I'm just following. Like it probably should be like a delta chi, but I'm calling it a d chi. It's got to be the least of our worries. And so then if I have a, oh yeah, let me go back. So remember, we just defined this map from K star mod L star to the abelianization of G. And I guess I didn't read this. Of course, you can pull this back to K star if you want. Okay. So, right. And so now I'm saying for an element of K star, fine, let's write A bar for its image in the quotient. And then there's the following compatibility. So if you take this map omega, what is that giving us? That's giving us an element of the abelianized Galois group, which is itself because the extension was already abelian. Then we hit it with a character, we get an element of Q mod Z. On the other hand, we're doing something else. So we're taking the coboundary, that's giving us something in H2 of GZ. Then we're taking the cup product with this guy, which again, this is a Tate H0. And so, okay, the cup product should come out in Tate H2, which is the same as normal H2 in L star tensor Z, which is L star. And so H2 of G L star is the Brouwer group of L over K. Okay. And then which is canonically isomorphic to Q mod Z via the invariant map. And okay, so at least I didn't prove anything, but at least this identity makes sense. Okay, and so yeah, this is it's the verifications get a little tedious, so and technical. So again, this is just a sketch of the proof. So I'm going to write V for the fundamental class. So I notice Harari writes U, but then if I'm not latexing something, like the distinction between U and the cup product is not fun to read. So I'm just going to call it V. Let's see. So S is just the image of this guy under, I mean, whatever, just S was naming that. And so that's an element of G, which again, I can view as I said, of H minus 2. Okay. N is the degree of the field extension. If you stop and think for it, I mean, the fundamental class is defined so that if you cup with the fundamental class, you get from H minus the isomorphism from H minus 2 to H, and whatever this omega was the inverse of that cupping map. And so again, you have to think about it for a little bit maybe, but immediately, by nothing other than the definitions of all these isomorphisms involved, if I take cupping with the fundamental class gets me from is basically is the inverse of omega. Yeah. Okay. That should be pretty clear, I guess. Okay, and so now we're going to use some properties of cup product, not all of which have been proven or even stated so far. So okay, so I'm supposed to be looking at A bar cup D chi. So A bar was V cup S. So okay, V cup S cup D chi. I told you before that the cup product was associative, so cup it in the other way. I didn't tell you this. It's in Harari that the cup product is kind of compatible with coboundaries when all that makes sense. But so trust me on this, that S cup D chi is D of S cup chi. That is explained very carefully. So you look back, and now, yeah, it does. Maybe it does suck. I don't know. S cup chi, however you want to read that. Okay. So let's see. So now where is this cup product going? It's going from H minus 2 with coefficients in Z, cup H1 with coefficients in Q mod Z. That's the character chi. So that's landing in H cup minus 1 with coefficients in Q mod Z. That's what this S cup chi is doing. Okay, so first of all, what is H minus 1 with coefficients in Q mod Z? H minus 1 is Tate H lower 0. So it's not quite the coinvariance. It's the sub guy of the coinvariance, which is the kernel of the norm map. Okay, but it's acting on the trivial module Q mod Z. So the augmentation ideal is a bunch of things generated by G minus 1, but G is acting as 1. So this denominator just goes away for any trivial module. And so what's the norm map is just multiplication by the size of the group if the module is trivial. And so therefore the kernel of the norm map is the n equals the size of the group torsion subgroup of Q mod Z, which is 1 over mz mod Z. Okay. So that's where S cup, I didn't evaluate S cup chi in any sense. I evaluated the group that it lands in. Okay, and so now there's a claim, and that is that S, it sounds good, right? Sux equals chi of S. Okay, you heard it here first, right? And so you think about this for a little while, and you say, yes, it does. It would make sense for this to be true because chi of S, what was S? S was an element of G. Chi is a character of G. Chi of S is an element of Q mod Z, right? And so yeah, it makes total sense for these two things to be equal to each other. And if you sort of think about it, it's like if I have some cup product of what else is it going to be? You would like it to be chi of S. That's not a proof, so I'm referring you back. This actually follows from, there's like a couple lemmas, and then there's a proposition. So this actually takes a little bit of a property of cup products that he develops. But okay, so Sux equals chi of S. That was very helpful. So now there's something else that I'm not really going to do in detail, but so suppose chi of s is equal to r over n. It's somewhere in the n torsion subgroup of q mod z. And so now what's the delta? What's the delta here, right? Because remember, I was supposed to delta of sux, and so now I'm doing delta of chi of s, and so this delta is really just one of these defining co-boundary maps for the Tate cohomologies. This is a very like smallest degree co-boundary map, right? And so if you think about it, there must nothing fancy. There must, I mean, this is a Tate H. This is just a map from an H0 to an H0. So this has got to be some totally explicit map, okay? And I'm not doing it. You can go back and see yourself. But if you evaluate this totally explicit map between this modified co-invariant group and this modified invariant group, then the claim is that under this totally explicit co-boundary map, delta of r over n is just r in Tate H0. And again, what is Tate H0? Well, it's regular H0, which is just z modulo the image of the norm map, which acts trivially, so it's z mod nz. Okay, so V fundamental class cupping with the co-boundary of sux is V cup with R, but R is just, this is now cupping with something in H0. And when you cup with something in H0, you really are just, how to say this? This is really just, I think this came up in long ago. Basic properties of cup products. Where is it? So yeah, so here's what happens when you cup with a zeroth cohomology group. It just gives you, it's basically just the map induced by, you're getting an element of AG, which is inside A. So it's induced from taking the tensor product with your H0 going from B into A tensor B. Okay. So really you are just kind of multiplying by the thing that you're cupping with. Right, let's see. Yeah, so especially here, because this R is actually just, it's just represented by an ordinary integer. So you cup with this, and yeah, so what was V? V was living inside of 1 over n z mod z, and so yeah, you're literally just multiplying by R. Okay, so we evaluate all that at last, and so the thing that we're supposed to evaluate turns out to be multiply the fundamental class by R. Now we apply the invariant map. R is an actual integer, so of course it's a group isomorphism. And so we get R over n, which is what chi of s was. What did we learn? We learned that the identity was correct. So the invariant of A bar cup d chi turned out just to be equal to chi of s, and s is what we called the reciprocity map applied to A bar. Okay, so that, again, it wasn't, there were a bunch of verifications, not all of which we actually made ourselves, but you can piece it together. Okay, and so here's the next one. This one is really important for the result that I was just telling you about. It's a kind of functoriality result. So what if you have one Galois extension? No, I don't have a tower written down, but I mean, you can certainly imagine. So I have K, I have L, I have M, and suppose the entire Galois group is G, and suppose that actually L is still Galois. So if I call it, so therefore this one is going to be normal, and then this Galois group is going to be G mod M. Okay. And so, so I claim that I have a commutative diagram here. So again, I have an inverse system on both sides, right? I'm going over, here at the moment, they're finite Galois extensions. The first step in the proof is going to be to say that we immediately reduce to the case where they're abelian. So imagine for the moment that they're abelian. So then I do have a natural inverse system here, right? So what are the maps on both sides? Well, aught of L over K, that's G mod N is certainly a quotient of G. And so, you know, if you have a homomorphism on groups, that gives you a homomorphism on the abylianizations, surjective homomorphism. Okay, so that's the inverse system on the group theory side, the natural one, right? The one that if I took the inverse limit over it, it would give me the abelian Galois group of K. And then I have over here, well, this just looks like a quotient map, and it is, and you just have to remember the transitivity of the norm. So for any finite degree extension, the norm from M, if I have something in the middle, the norm from M down to K is the norm from M down to L, followed by the norm of L down to K, just basic field theory. And so by nothing, of course, the norm of M down to L of M star is contained inside of L star. So the norm from the bigger extension is going to be a subgroup of the norm from the smaller extension. So I have a quotient map. Whenever you have one subgroup of another subgroup, you have a quotient map from modding out by the smaller subgroup to modding out by the larger subgroup. Okay, so that's the point. This is what makes the inverse limit that I just talked about make sense. Okay, you have inverse. We know we have isomorphisms, right? And now I'm saying that the isomorphisms are compatible with this inverse system. Okay, yeah, and here's where unfortunately I found the proof to be possibly a little bit fishy, or possibly I just didn't. I mean, I have not gone back and read every single word that Harari said about cup products, so maybe I just missed it. But okay, let me write out as far as I got with it. So you have an element in K star, so no problem. Let's have A bar L be its image in that quotient, A bar M be the image in that quotient. I don't really like the word baby. On the other hand, there's just a duality. It's not even Pontryagin duality. It's just the duality theory of finite commutative groups. So aught of L over K. Oh, I forgot to say this. I forgot to say this part. I said it before. If you think about it for a little while, if you just replace each of these not necessarily abelian Galois extensions by their largest abelian subextension, you immediately reduce to that case. Okay. Evidently, if you do that, you haven't changed anything on this side. That's kind of what you're doing. You're literally reducing to the maximal abelian. You're only looking at the maximal abelian subextension. That is what the abelianization is. And you think about it a little bit more. If you think about what we just proved, then everything that is a norm from M is already a norm from the maximal abelian subextension. In other words, the image of this norm, not even that, the image of this norm map is pretty clearly also equal to the image of the norm from the maximal abelian subextension. Okay. Yeah, so you reduce to the case where M and L are both abelian extensions. And so now I have one abelian group, finite abelian group surjecting onto another abelian group. And then if we take character groups, which is just Hom into Q mod Z, right? Then it's a duality, so it goes the other way, right? And so this injection on finite abelian groups becomes this surjection on finite abelian groups becomes an injection on the character groups. What am I doing? I'm just pulling back. So if I have a character defined on the quotient G mod N, then I just pull it back to be a character on G. I just pre-compose with the quotient map from G to G mod N. And this embeds the character group of the quotient as the subgroup of the character group, the subgroup of characters that are trivial on the subgroup. So that's fine. Right, and so we have one character group being embedded in another. Harari doesn't do this, but I decided to be slightly careful. So I just gave you an injection from the one character group to the other character group. Let's just write chi sub m for the image of chi under this injection. Okay, so now this is what he says. He says, we just proved this identity, no, that's exactly what we just proved, right? Yeah, so we just proved that this reciprocity map, and then you apply any character, and then you get this thing with the invariant map and the cup product. Okay, so we certainly have that. And then he says that this invariant map is equal to the same damn thing, except you replace the L's by M's, basically. And then you do it the other way. Okay. And then if this is true, then this holds for any character of groups. I'm trying to show, again, I'm trying to show the commutativity of this diagram. And so if you think about it for a little while, it's fine. If the commutativity holds after applying an arbitrary character, then because of the duality between a finite abelian group and its character group, then that's certainly gonna be good enough. And so since these things are equal after applying any character, then you get, well, not exactly that they're equal because they don't quite live in the same place, but again, what is this guy? This guy is living in G, the automorphism group of M over K. Once I assumed it was abelian. This one is living in the quotient, and so what this identity is telling me what I want. It's telling me that that this guy in the quotient is the image of the guy in the original group. Okay, but you see that there's a star here, right? So why is that true, right? And that really is it. Everything else seems. I mean, we could explain a little bit more maybe about why it's okay to apply a character, but that's kind of the least of our worries. And so this is where I got a little stuck. So he says bifunctoriality of the cup product is why this identity is true. And it's like, well, exactly what do you mean by that, right? The cup product has lots of functorial relationships. Why don't you say by proposition 2 point something or whatever, right? And so I wrote this out a little bit. And so this seems to be the situation. So we have this norm surjection here, the thing on the left side. This is the Tate cohomology group here. This is M star, sorry, this Tate cohomology is K star mod norm of M. This Tate cohomology is K star mod norm of L. This is a Tate cohomology group of G. This is a Tate cohomology group of G mod N. So there is a map here. That is our quotient map that so this map here is exactly what this map is here. On the other hand, so what am I doing? I'm taking cup products, right? So I'm taking this type of cup product. This A bar is living here and here, so that's why I wrote that one. Then I'm cupping it with the co-boundary of a character. So the character is in H1 and Q mod Z, so its co-boundary is in H2 of Z. So again, the character co-boundaries live here and here. Okay, and there is a natural map in the other direction. That's just an inflation map. Okay. And then where are they going? They're going, before I take the invariance, they're landing inside the Brouwer group of K. Or a relative Brouwer group, which is a subgroup of the Brouwer group. And so again, if you just do the cup product, then they land inside of H2G of M, which again is the Brouwer group of M over K. And this one lands inside there, which is the Brouwer group of L over K. And again, there's an inflation map. Okay, so I drew the diagram, right? And so now the functoriality of the cup product should say, I mean, it looks a little strange the way these arrows are going, but it's all okay. And so, I was all set for it to find this diagram in his discussion on cup products, and then that would give me the compatibility. So I didn't find this. This map here looks a little bit strange. These are inflation maps, and this one is going in the other direction. So maybe you'd want to call this a deflation map. That wasn't my idea. He actually does define a deflation map on remark 4.29 on page 76. But yeah, so I don't know. Maybe I'm wrong. Maybe I'm looking at it wrong. It's very, very possible. I totally think that this diagram commutes, and the result is what does it mean for the diagram to commute? It means this. It's exactly what we're trying to prove. I just didn't find it. However, I found a similar dual diagram, which maybe I'll show you. Let's see. I mean, it's also in it's in the proof of a statement of a result, but maybe I'll just show you the I'll show you the statement. Right. Yeah. So this, can you see this?
Yep.
Yep.
Yeah. So yeah. So this is in the. Maybe I should show you to prove E. So what is E? Yeah, it's some compatibility with the cup product. So you see, it's very similar, but apparently dual to what we're trying to prove now, right? We have subgroups and we have modules, and this is some kind of like res co-res compatibility here. But you see, it's sort of like, you know, you do this one and you, you know, you have two co-reses and a res, okay? And they're compatible. And then what's the diagram that you're looking at? Well, in particular, he's looking at this diagram, okay? And I'll switch back in a second, but it's pretty similar. I think like all the arrows are reversed. Yeah. Well, the way I drew it, okay. I have it in my diagram, I'll show you in a second. I have a down arrow, an up arrow, followed by an up arrow, where he has a down arrow, and up arrow, but okay, you could switch these two. That'd be fine. I mean, this one is good. Here he's got two H0s, so whatever, you switch them the other way. And so if you think about it, so this is a res co-res funny compatibility. I want an inflation deflation funny compatibility. So it kind of does feel similar, you know, dual to this one. And so yeah, so that's kind of as far. And then it was like really late last night, and I was just like, okay, well, that's where I got with it. Yeah, so let me share. I mean, so of course, like the result is true. Like it's 100% true standard result. When I get a minute, I'll just look and see, you know, in some other treatment of class field theory and see what they say about it. But yeah, no. So I this bifunctoria. Yeah, you see that my diagram is kind of the dual of this. Yeah. So I don't know. Yeah, I can't decide whether I'm kind of writing it out, not, you know, in a correct, but this is not the way to write it out to make you see that it's true. Maybe it is a more evident property of the cup product that I'm making it out to be. Cup products are not my strongest point, if I'm being honest. Anyway, but so I'm sure it's definitely a true result, and maybe a way to prove it is to try to prove this dual version of this res co-res thing that he proves for the cup product. Okay. Anyway, so you know, check question mark. But yeah, this is a standard. This is a standard compatibility. Okay. Right. So that proves that, and that was what we needed, like I said. So now, you know, whether we proved it or not, we're now logically at the point where we have our inverse system with surjective maps between the finite groups here. We certainly have our inverse system with surjective maps between finite commutative groups here. Same over here. And so once we have that compatibility, that's exactly what we need in order for the isomorphism to pass to the inverse limit. And so now, again, now we have this reciprocity map from K star into the profinite completion, sorry, the abelian Galois group of K. And then the rest of class field theory, well, I mean, the main part of it is to show that this reciprocity map omega is actually a profinite completion. Okay. Which is a little bit fancier than it needs to be, because K star is almost profinite already, right? So K star, once you choose a uniformizer, K star becomes isomorphic to well, the unit group, which is profinite, cross Z. So we've done that. Again, this is just, you take an element of K star. After you choose a uniformizer, then you can write any element of any discretely valued field as a unit times some power of the uniformizer. Okay, and so this guy is profinite. And so it's not very mysterious what the profinite completion of K star is. You tell me, if K star is U cross Z and U is already profinite, then what's the profinite completion of K star?
U cross Z hat.
Yes. Okay, so the profinite completion is basically just replacing the Z by a Z hat here. Okay, let me end this lecture. I'm just stating a couple of results without proof, but yeah, let me maybe just skip to the end. And so one of the results here, so what if we have an unramified finite extension? Then the Galois group is canonically isomorphic to the Galois group of the finite residue field. So it is abelian and even cyclic, because all Galois groups of finite extensions of finite fields are cyclic, canonically generated by the Frobenius. And so then the result is on an unramified extension, again, you have F, which is, again, this group is, we've done this before, the automorphism group of the unramified extension is canonically isomorphic under reduction modulo of the maximal ideal to the automorphism group of the extension of residue fields. And so if the residue field of capital K is little fq, then the element has a canonical generator, Q power Frobenius, and let just plain old F be whatever element, the unique element of the upstairs automorphism group that maps to the Q power Frobenius under that isomorphism of groups. And so this result is saying that no problem to tell you what the reciprocity map is on an unramified extension. It really is just a certain power of the Frobenius given by the uniformizer. Okay. Moreover, if you take the entire reciprocity map and you evaluate it on the unit group, which again is the more interesting part, then the image is the entire abelian inertia group. So it's the Galois group of K-ab over K on RAM, which of course is sitting as a subgroup of the automorphism group K-ab over K, which is the abelianized Galois group that we're saying. So what am I really saying here? First of all, I'm saying is that we don't need class field theory to tell us about the unramified abelian extensions of our local field. You know, the unramified extensions of our local field are isomorphic to the extensions of the residue field. It's Z hat. You know, we know exactly what we have. We want class field theory to be telling us about the ramified abelian extensions, and the answer is that this group, again, there's a splitting here, and the Galois, I'll say more about this next time, but the actual abelianized Galois group is isomorphic to the inertia group cross the Galois group of the maximal unramified extension. Okay, and so that's what's happening on the Galois. It would not be at all hard to show. I will do that in the next lecture, I guess, to show. Yeah. So my claim is that ought of K-ab over K. There may be a choice here. I'm not saying it's a canonical isomorphism. In fact, I don't think it is, but you can write this as ought of K on RAM over K direct sum ought K ab over K on RAM. That's what I'm saying. So I'm saying basically I have this tower K ab, which you can't see, down to K on RAM, down to K. And so this one is Z hat, and this one is what I was calling the abelianized inertia. And so what am I saying? I'm saying that this extension is split, and so it should be a semi-direct product, and it's abelian. So the semi-direct product is direct product. So I'm saying that this is a, so I have this short exact sequence. Let me get it right. So 1 goes to IK-ab, goes to abelianized Galois group of K, goes to Z hat, goes to 0. By the way, it's actually split even before you take the abelianization. That's a fairly, it's part of number theory too. So the claim is that the sequence is split. Well, okay, it kind of has to be split because this is a Okay. If you covered up everything else and just looked at this as a short exact sequence of profinite groups, whatever the analog of projective modules is in the category of profinite groups, it is actually called a projective profinite group. Z hat is a projective profinite group. So for purely group theoretic reasons, this sequence has to be split. Okay. So right, and so you see that there's but the Z hat is canonically a quotient, right? I'm saying you can find some sub extension which realizes it as well, although it is canonically a quotient. Anyway, and so you see kind of that you have these two pieces. You have the unramified piece and you have the totally ramified piece. That's where the Z hat is coming from. And so you go back over here and you have this profinite completion. And so again, this Z hat is going to be isomorphic to the automorphism group of K on RAM over K. And this one is isomorphic to the abelian inertia group, which is the automorphism group of K-ab over K on RAM. Okay. So now we're talking local class field theory. Okay, so what I'm saying is the fact that we're passing from K star to its profinite completion is like not a big deal at all. It's kind of like saying, because the valuation has to be an integer rather than a profinite integer, we have to take the profinite completion. Okay. I think this is a good place to stop. Yeah, any final questions? I think it's definitely worth just like trying to ask yourself, like, how does it all fit together? Where are we going with this? You have to ask the, I mean, you know, I also want you to like look at the details of it, because, you know, how do you do something without looking at the details of it? But I think it's like, don't lose the forest for the trees. I think, you know, I think we're in that situation at this point. Okay, so I think next time I'm gonna state a few more results. And then there's this really nice approach due to Lubin and Tate, which again is it's kind of like the Lubin-Tate's approach is kind of like the analog for local class field theory that the theory of complex multiplication gives you for explicit class field theory of imaginary field, and then just like cyclotomy gives you for just roots of unity give you for class field theory of Q. And so Lubin and Tate had this amazing idea that if you use formal groups and stuff, and you use torsion points in formal groups, which is also sort of a standard, Menzellis knows about torsion points in formal groups. And so yeah, so this is a kind of explicit class field theory for local fields rather than two very specific number fields where, you know, anyways, that's what's coming. And I think I would be happy to just like really develop Lubin-Tate stuff for like a couple weeks. I think that'll be a good use of our time. Okay, see you soon. See you tomorrow maybe for the tea.